So we were doing PL condition last class, and so we will continue from there. So as I said, PL condition is a more general condition than convexity, and we have seen strong convexity, and we saw that PL condition is like this. So from this it seems like some PL may not be convex, but all PL are strongly convex. Okay, so there is an extension away from convexity, prove some guarantee in convergence. Okay, so that's what we have done. So what we have done is a mu strongly convex implies mu strongly convex implies mu PL. Okay, so I think we have done this proof in the last class, and then I gave you an exercise that you have to prove that t square plus 3 sine t whole squared is not convex, but it's PL. Okay, that's why we have that diagram. Okay, so there can be, so it is not convex but PL. And then we have also seen that if we have fx defined to be an L2 loss, which is phi x minus y norm squared, and phi goes from Rd to Rn, then what could be the PL condition in this case? Okay, and we characterize that the PL condition would mean that the lambda min of d phi transpose is greater than equal to mu. So what we have said is that if d phi x, okay, d phi transpose x is uniformly injective, so that's the characterization that lambda min is greater than equal to mu, is uniformly injective, then phi is PL. Okay, so this is also we have proved last time, and uniformly injective means that the lambda min of this transpose with itself is greater than equal to some mu, which is positive. So and this could be any nonlinear function also. Okay, so for instance, this can be applied to neural networks. Okay, so phi can be neural networks. So if you can do this Jacobian calculation, and okay, phi transpose and phi, and somehow prove that the lambda mean is bounded by mu, then it will be PL. Okay, and if it is PL, then we will prove that it guarantees convergence as well. Okay, so there are local inequalities also with the same guy. Okay, so it's hard to pronounce this name. So there are like more general variant of these inequalities as well. So these inequalities can be, yeah. So before this there is a result. Let f from Rd to R be differentiable PL function, then x star in arg min of f if and only if grad f star is 0. Okay, so there is this result. If f is differentiable and PL, okay, then x star is the minimum, it gives you the minimum if and only if the gradient vanishes. So this seems to be very similar to the convex, okay. So convex was also like that, right? If x star gives you the minima, then grad of x star is 0, and if grad of x star is 0, then x star is the minima, okay. And this we can prove because we did an inequality before, which, I mean, not the inequality, but I mean the definition of the PL itself. So if you recall the definition of the PL, then it was fx minus infimum of f is less than or equal to a norm of gradient of fx squared with 1 by 2 mu. So this is the definition of PL, right? Of a PL function satisfies this. So if I have to prove this theorem, then if gradient of fx star becomes 0, then obviously this guy, which is greater than or equal to 0, right? Because this is the minimum possible. So for any x, this must be greater than this. So this quantity is positive, and the PL says that it's less than or equal to this. So if grad vanishes at x star, then this means that fx minus infimum, which lies between 0 and 0, would mean that it is equal, right? So fx becomes infimum, right? So we can write this. So if grad f x star is 0, okay, for this x is equal to x star, then clearly then this implies fx minus infimum of f is 0. This implies fx is indeed the infimum of f. In other words, x is the argmin of f, right? This implies x is in the argmin of f. So this is the star, I mean, this is the same star, right? Okay. So if for x star, grad f x star is 0, then and this happens. Actually, this is if and only if. Okay. So the other way is also. So here I assume that grad f x star vanishes, then x is the minimum optimal point, and then if x is the argmin of f, then this quantity will be 0. So okay, the other way around, how do we prove, right? If x is in the argmin, so let us do it this way. We did this way. So if x is in the argmin of f, meaning f achieves minimum there, then I mean at x star, then what do I have? I have that fx star is a minus infimum of f is 0. Okay, so how does this prove that grad f will be 0? Grad f seems to be greater than equal to 0, right? But we are supposed to prove equal to 0 because it's if and only if, right? So it should happen both ways. If x star is argmin, then fx star minus infimum of f is 0. Derivative must vanish, right? Because that's the minimum point, right? We don't have to really do anything from here, right? This is exactly right. So this is infimum of f. So this is like evident, right, that for any function to have a differentiable function to have minima, it's evident that grad must vanish, right? So we can, like, yeah, it follows straight away. Okay. So yeah, now we go back to this local inequality. These are just remarks, like we are not going to use this immediately. So since we are not going to use this immediately, let me skip it, okay, because there is no point in, like, we will, if we need it, then we will do that, but there is no point to do it now. Then let us define something called smoothness. So let f be from Rd to R and L greater than 0. We say that f is L smooth if it is differentiable and if gradient of f that goes from Rd to Rd is L ellipsis. Okay. So we have seen ellipsis condition. Here it's we are saying L smooth. Okay. So ellipsis continuous, and then this is ellipsis smooth. So basically it will be applied on the gradient of f. Okay. So now so this happens if for all x, y in Rd, the grad f x minus grad f y is less than equal to L norm of x minus y. The usual ellipsis continuity, we have fx minus fy less than equal to L x minus y, but L smooth is grad fx minus grad fy is less than equal to L x minus y, where smoothness is refers to the gradients. Okay, that's why sometimes we say non-smooth function means non-differentiable. Okay. So this is one of the property which could be used in the proof. So we can also characterize L smoothness in a slightly other way. So if a function is L smooth, then it can satisfy some other property as well. So let us see that. So if so maybe this lemma was D. So if f goes from Rd to R is L smooth, then for all x, y in Rd, fy is less than equal to fx plus grad fx y minus x plus L by 2 y minus x squared. Okay. So remember when we were doing strong convexity, we had a sign greater than equal to, and then there was a mu or something, right? So what we are essentially trying to say is we have both the bounds. Okay, we have one of the bounds. So what we will do eventually, right? We have strong convexity. So that was with the same guys, but mu by 2 norm x minus y. So that gives us strong. So that's the lower bound, and now we are heading to the upper bound, okay, which is called smoothness. Okay, so that guy here is the upper bound. So with this bounds on the function, okay, you have some behavior of a function that is nice for convergence. Okay, in general, convergence proof may not be tractable, but if we have this strong convexity or smoothness, then we can prove some results, and later we will extend this to PL condition also. Okay, so for the moment we will prove results with smoothness and strong convexity. So let us now prove this result that if indeed f is L smooth, then this inequality holds. So proof of lemma d. Okay, so let xy, we fix xy, so let x comma y in Rd fixed, let phi t be f of x plus ty minus x. Now we will use fundamental theorem of calculus on phi. Okay. So using we see this as fy being computed for f, so fb minus fa, okay, and definite integral, right? So fe minus fa is equal to integral of the antiderivative, all those, right? So that's what is our plan, okay? So but it's on the single variable because we characterize this by phi t. So let us do that. When I write, you will recall all this. So what we recall from the fundamental theorem of integral calculus is this, which is nothing but the way you calculate the definite integrals, right? Or this is another way to say that fb is fa, the initial point, plus from a to b ft dt, where ft is the antiderivative. Okay, so we are going to use this, and we are going to use this with b1 and a0, and our f will be phi. Okay, so you keep this in mind. Now what we are going to do is that you use f phi. A we define it to be 0 and b we define it to be 1. Okay, and then it will say that I want fy, right? A 0 t0 will give me fx. Okay, should I, is it okay with fx? No, I think I should go with fy, right? So and it should be t equals to 0. So then I should choose t equals to, yeah, the corresponding values, right? I mean, it doesn't matter. It's a matter of like what I really want, right? So in this case, like a is like y I want, okay, and b is x I want. Now a y is achieved when, so then I have to integrate from 1 to 0. It's fine, like I will do the negative of that. Okay, so t that corresponds to t equals to 1. Then yeah, so I will write down and then relate to that first, okay, because we want it in a way that is useful for us, right, which is fy. Okay, so fy is fx plus t equals to 0 to 1 grad f of x plus t y minus x dt. Okay, that's phi 1 is equal to phi 0 plus t equals to 0 to 1 phi prime t. Okay, so I just related things for you to match with what you know as a fundamental theorem of calculus. This is what we did, okay? So at phi 1, at for t equals to 1, you have fy. For t equals to 0, you have fx. And in the integral, you will do t equal to 0 to 1. And phi prime t is like you have to take the derivative of this guy. So derivative of this guy, you apply the chain rule. So gradient of this, okay, times, so phi prime t, I have to take derivative with respect to t. So this is grad f of x plus t y minus x. And then I have to look where inside the derivative of inside terms with t. This is the chain rule, right? So this is like this transpose, these are vectors, right? So this transpose, and what comes out after is y minus x, which is written as an inner product here, okay? So x transpose y, right? So I can write this as inner product of x, y. So f x plus t y minus x and y minus x, okay? So this is what we did, right? So we are supposed to prove this. Fy is less than equal to fx, okay? So we have to go there. And f is given to be L smooth, meaning this thing holds. Grad fx minus grad fy is bounded by L norm x minus y. So the way we may get this, it seems like we may first have an inequality. So what is an inequality that you know on inner product? So what is an inequality that you know that applies on inner product? Is less than equal to, what was that from linear algebra? Cauchy-Schwarz, okay. So Cauchy-Schwarz is norm x, norm y, okay. So we have an inner product there, and it seems like this integral will be dominated by the integrand will be dominated, or it's like greater than norm x, norm y. So in this case, our norm grad f, norm y minus x. Okay, so that will make it less than equal, but still we have to figure out a few more steps, because the way we have to use is this guy, right? There is like some difference is less than norm x minus y. So the grad term that we have somehow should split, somehow should give us another y minus x, so that the one that came from the Cauchy-Schwarz y minus x and something that comes from the one of the other terms with grad f, those combine, I believe, might give me like one of them will stay, and the other one should somehow like y minus x transpose y minus x, that will give me this. So we have a little bit of sketch right now. We can see how far we can simplify more. Yeah, there will be square. Yeah, right, there is a square here, right? Okay, so these are these initial things. Let us see how far we can go. Okay, let us see how far we can go from here. So there won't be square, right? Okay, so okay, there is no square, right? Right. So so certainly, yeah. So what we have now is, okay, the proof does a, okay, interesting. The next step in the proof here is okay, grad f x I c plus t y minus x I c, and then why did it subtract grad f x? Okay. Okay, let me write down then. So fy is less than equal to fx plus grad f y x minus y plus t equals to 0 to 1 grad f x plus t y minus x minus grad f x y minus x dt. Okay, so there is this step done in the proof, and this is less than this is not less than right now. This is just equal. Okay. So it seems to me that add and subtract has happened, but if I look into the integral, then this step seems to be looking very off to me. Fx, then okay, our previous term was y minus x, that's fine, and grad of xt y minus x, that's fine. We have introduced a negative grad f x, but then if we have introduced that, then we have to compensate for that. But does this term, that additional term, second term here, does it compensate that, right? Okay, very interesting. I mean, I have no idea here what just happened. If I just split this, right, fx plus grad fy x minus y, the additional term that that was here is minus, so we have to like do a reverse thing here. So the additional term that we have is grad f x y minus x. Okay, so if you see, these guys are additional. Okay, and the remaining terms were from the previous step. So this is plus 0 to 1, and this is like inner product. So inner product grad f x plus t y minus x and y minus x dt. Okay, so these guys are introduced. Now if they are introduced, then they have to be 0, because that's an equality, right? And this integral doesn't mean anything, right? There is no t also, right? So this comes, this will be just the same thing. Even if there is dt, this guy just comes out. You integrate, that is t, and t integrated between 0 and 1 is just 1. So this integral can just be removed. Okay, so so what is left is this minus or plus minus, right? Or if they if the two arguments cancel, that actually it will be okay. Now I'm wondering, like x, so I am expecting this to be plus, because if it is plus, no, well, how can it, no, it won't work even that way, right? I need something common to add inner products, right? So yeah, that's fine. Okay, so if I have a minus here, then this becomes x minus y, and even then, right, so let us say that we make this plus, right, because we take the plus inside. So this becomes x minus y. Okay, this becomes x minus y, but still I don't see them going to 0, right? So this becomes grad fy plus grad fx comma x minus y, but still this doesn't seem to be 0. Grad fy x minus y and grad fx, it was minus grad fx y minus x, but then minus we took inside, so it is x minus y. That's fine. So even this doesn't seem to be 0 to me. What is given is L smooth, but L smooth does not give us this term to be 0 yet. It seems to me. L smooth doesn't give me 0 here, right? I have no idea why it should be true.
Sir, how did we add that term still keeping that equality?
Here, right?
Yeah. Like
Yeah, this is what we are trying to understand, right? This is exactly what we are trying to understand, why it is equal. Okay, this is a question mark here. So until here it's fine, and then the next step in the proof is, so basically we went from here, this was our first step, okay? But then in the next step, the proof says that this will hold. But yeah, it's not clear how. If it was fx, then it makes sense that it will be 0. There could be a typo actually. We may be trying to figure out a typo here. If it is fx, then what happens, right? And there is a minus there, right? So minus grad fx and y minus x. Yeah, for it to cancel. Yeah, there may be typo also, but that's the point. Let's see what can be done. So if I have, let us try to fix this, okay, in our own way. We don't know whether we will be in a good shape or not. So let us say I subtracted because I wanted to. Then to cancel this out, I must have the positive of that. So meaning I must have fx and y minus x. And I know that they will get cancelled, okay? So from the inner product, minus inner product grad fx y minus x and plus inner product will get cancelled, okay? Let us see if we go from here. And okay, and if anyway, like so this will be less than equal to, and then the trick is to apply Cauchy-Schwarz here. Okay, so then we have fx plus, we just copy this, grad fx y minus x plus t equals to 0 to 1, and yeah, Cauchy-Schwarz will be norm of grad f x plus t y minus x. Okay, the benefit, the reason why we have done this is to use the L smoothness, because in L smoothness we needed grad f y minus grad f x is less than equal to, okay, so we needed some form of a difference here, right? So here we will get that, right? So grad f x and norm of y minus x dt. Okay, so the integral, if we know that f is greater than equal to g, then the integral of f is also greater than equal to integral of g. So this is what we used here, right? Okay, so it seems like this is a place where we will apply the L smoothness. Okay, so let us continue. So this will be less than equal to fx plus grad fx y minus x plus t equals to 0 to 1, and this will be L of the norm of the difference of the arguments, right? So this is like L of the norm of the difference t y minus x minus x, and this is norm y minus x dt. X gets cancelled, right? So, and we are left with t, and norm of y minus x times norm of y minus x, we have a square of that. So this is equal to fx plus grad fx y minus x. Okay, if you see the way this term appeared, right? I mean, it was good idea to put this, right? Because we saw this, right? We had this in the term in the proof. We had to do that, right? So this is why we do this. I mean, what we need, we add and subtract if we don't see it here. Okay, that's a generic technique that we follow. Okay, so you may say, why did they do that? Because you had this to be proven in the theorem itself. Okay, so maybe I have I don't have that, right? So what we are trying to prove is fy less than equal to fx plus grad fx y minus x plus L by 2 norm x minus y. Okay. So we started with that, right? We started with this, and there were two things, like we wanted this difference to be seen so that we can apply that L smoothness, and this term was missing. Okay, so these are the ways, like you see what could be done in the proof, right? So we saw that adding that second term on the RHS, adding and subtracting does this trick. Okay, so that's why it's done. So you see these two terms, and certainly you see the third term also, L by 2 norm y minus x whole square, right? So this is, we don't, oh, t is there, so there will be t square by 2, then we will get 1 by 2, right? So norm y minus x whole square comes out because there is no dependence, and inside you have integral 0 to 1 of t dt, and that certainly becomes, this whole thing becomes half, and that proves, and L also came out. Okay, so this is what we were supposed to prove, right? So now let us prove lemma E. So it's like 3 classes, we will just keep proving. Okay, it's kind of a crash course on just proving things for 3 classes. After 3 classes, then you will see a lot of new algorithms also. Okay, so lemma E, so f from Rd to R is twice differentiable. So this is giving us a hint that we might be using some Hessian at some point, right? So it's twice differentiable L smooth. Then for all x in Rd, so remember when we were discussing Lipschitz continuity, right? So Lipschitz continuity told us that fy minus fx is less than or equal to L x minus y. So if we can find a constant L such that this happens, then we say that f is L Lipschitz continuous, and a consequence of this, we have proved that, right, was grad fx norm is bounded by L. Now we are trying to do the same thing for now L smoothness. Okay, so in L smoothness, f is L smooth. Now this told us that grad fy minus grad fx is less than or equal to L norm x minus y. So you can already make a guess, right? Here your f was like that, then your grad was less than L. Now your grad is like that, then your grad of that grad will be less than L. Okay, so that's what we are trying to prove. Okay, but in this case, the norm will signify norm because I will take a grad of grad, it will become a matrix, right? So that will be like a Hessian, right? Now we have to use the matrix norm, right? And we have to say that the matrix norm E is less than or equal to L. So if we are using a suitable norm in a way that that norm signifies the eigenvalue of a matrix, right? So 2 norm, for example, then this will kind of characterize that even the maximum eigenvalue of the Hessian will be less than L. Okay. So this is where we are going. Okay. So now let us see the. So this is what this lemma will try to show now. Okay. So then for all x in Rd, for every eigenvalue lambda of grad square fx, we have so that's what I said, right? That if f is L smooth, then it is necessarily true that the eigenvalues of the Hessian will be bounded by L. Okay. So now let us try to prove this. So we will recall effect for the Lipschitz continuity, which is exactly this. Okay. So if f is L Lipschitz, then so this is like f is L Lipschitz if and only if the gradient of f x is less than or equal to L. I already said that here, but in the full proof or in the main proof also I just kind of like copied it here, okay, because this is what we are going to use. So in this we will substitute f with grad f. Okay. So substitute f by grad f. So so obviously like it is not 1, but it is like L. Okay. So so obviously if we do that, then we have that norm of grad square f is less than or equal to L. So what about the eigenvalue bound, right? So let us do that. So then for every eigenvalue I mean, you can again use the Rayleigh quotient, right? Like we have done several times, right? So this is a matrix induced norm, and this is given by the supremum, okay, supremum of. But yeah, so this is given by but the Rayleigh quotient is for, yeah, it makes sense for symmetric, right? So one way is like this, lambda max is supremum over u transpose grad square f u by u transpose u. Okay, so we have used this on several occasions, right? And we know that it is max for u, which is the largest eigenvector, right? I mean eigenvector corresponding to the largest eigenvalue, and the norms, the way they are defined, right, the induced norms, they are defined as the ratio of grad square norm of grad f u divided by norm of u. Okay, and if it is a 2 norm, then 2 norm exactly characterizes lambda max. okay, but for any other norm it's not true. So one possibility is to prove in that way, okay. But for a generic proof we will do it now, okay. So for every eigenvalue, so for every let us say non-zero eigenvector, okay, non-zero eigenvector, and lambda is the corresponding eigenvalue, lambda corresponding eigenvalue, then what do we have, right? So let us consider this. Now this is norm lambda v, and this is grad square fx v, okay. So I have said that lambda and v are the eigen pair, right? So all this makes sense, all these quantity makes sense, right? Now this guy is less than equal to grad square fx, and which is less than equal to L norm of v, okay. The norm of the product less than equal to product of the norms, and grad square fx was bounded by L, so I have that, and v being an eigenvector is non-zero, right? So I can divide by that on both sides. So dividing by which is non-zero, so I have that mod lambda is less than equal to L. So a function being L smooth means that its eigenvalues are bounded, okay, by the L, and these are the bounds we need, okay. So function being very I don't know how to say, right, very bad is hard to optimize, okay. By bad, what do I mean by bad, right? So when its eigenvalues are very stressed out, okay. So for instance this is bad, okay. These are the level curves of the function that I am working with, okay. Then it means that the smallest eigenvalue is this and largest eigenvalue is this. So there is a lot of stretching in this way, right? So these are the problems where gradient method will find it difficult to converge, okay. It may do a lot of oscillations, okay. So it may go like this, then like this, then like this, then like this, and so on. What is the perfect case? Perfect case is when eigenvalues are the perfect is the circles, right, the identity. So in that case, so you go there and you go directly to the minima, okay. Yeah, no, this is from here itself, right? If f is L smooth, then grad f is ellipsis continuous. So it's like f being L smooth is like saying grad f is ellipsis continuous. So grad f being ellipsis continuous means grad of fx must be less than or equal to L. The another result is that if f is L smooth and mu strongly convex, now we are trying to combine both, okay. And so how can you relate mu and L? F is mu strongly convex and L smooth. So what can you say about mu and L, right? Is mu greater than L? Is mu less than L? These are the basic techniques for proving results. So that's why it's good to do it once, because they just keep repeating. I mean, you develop a new algorithm, you just use the same framework but just modify a few terms here and there, prove some inequalities, and So usually what happens, even if you develop new algorithm, it's good to justify. So when you write scientific papers, people expect that you are not doing things like engineering. They expect that you justify few things, even if it's for ideal case, even if it's for some Lipschitz continuous, mu strongly convex, PL condition, but they expect that. That's why research is like different from engineering. Okay. Some guarantee is needed, complexity analysis, things like that. Okay. So remark that we write is if a function is L smooth and mu strongly convex, then mu is less than equal to L. Okay. Let us now try to see both together. We have studied strongly convex in last class, and we are trying to do L smoothness now. So if we combine both, then I can write, so Fy is somewhere here. This is upper bounded by Fx plus grad Fx y minus x plus L by 2 norm x minus y whole squared, and this is L smoothness. And in the mu strongly convex, Fx plus grad Fx y minus x plus mu by 2 norm y minus x whole squared. Okay. So looking at this, this is the mu strongly convex, and this guy is L smooth. So now from this, the remark is clear that mu must be less than equal to L, because the only difference you see in left hand and right hand side is coming from here, and in fact the only difference is this. So it must be that mu is less than equal to L. And if the function is twice differentiable, then mu strongly convex means that the minimum eigenvalue is greater than or equal to mu, and we have just seen that the maximum eigenvalue will be less than or equal to L. So in other words, strongly convex and L smooth is telling you this, lambda of this, the eigenvalues are lower bounded by mu and upper bounded by L. Okay, and this is the grade, I mean the Hessian. So when proving convergence results, we are asking for Hessian to be well behaved. Okay, it does not have, I mean, well behaved in the sense that when we will, let us say we go and prove some convergence result, this L and mu will show up, and very large the L is, the convergence will be bad. That will be seen in the proof, in the final result. And similarly, if mu is very, very close to 0 also, we will see that the convergence will be bad. Okay. So the number of iterations that you will need to get certain accuracy will be very high, because mu will be in the denominator. So if eigenvalue is very close to 0, so the number of iterations that you are going to do, okay, we will kind of prove this, but it will look like that. Okay, there will be few more things here, but it will be like that. If your eigenvalues are very bad, number of iterations will grow. If your largest eigenvalue is very, very big, also number of iterations grow. So what this tells you is if your Hessian is identity, then the convergence is in one step, because number of iterations will be order of 1. Okay, there will be some constant, let's say, but that is still like not too high, I believe. Okay, couple of iterations. But this directly corresponds to what I told you just now, is that functions eigenvalue being bad means their level curves are so the best level curve is like this, right? So if I look at the level curve here, then so level curves are the projections of these on the domain, right? You are looking for your solutions on the domain. Okay, so you are searching for the minima. You see here, oh, okay, this is very high, and then you do the gradient, and then you go here, and then you go here, and so on. In this case, it will be very straightforward to converge. Okay, but if your function is not well behaved like that, and then your level curves are also like that. Okay, then in the gradient you will be doing lot of this, which means that it will be slow to converge. Okay, and this is characterized by eigenvalues being very not proportional, I mean not very close, because there is a stretching in some directions. Okay, things like that. So that's a, in fact, people define something called condition number, which is the lambda max of the Hessian by lambda min. So lambda max of grad square f by lambda min of grad square f. Assuming that it's a symmetric Hessian, then lambda max and lambda min will be real number. So this is called condition number of your problem. Okay, if you're trying to find a minima of that, and if you have hold of an Hessian, then by taking this ratio of lambda max and lambda min, you can more or less say how bad your algorithm is going to perform. Okay, and these things are in some sense characterized by smoothness and strong convexity. Okay, that's very kind of connected to the largest and smallest eigenvalue. The ideal mu that you are looking for is lambda min, and the ideal L that you are looking for is lambda max. But the problem is, you may not, in practice, it may not be feasible for you to find this L, because it requires solving an eigenvalue problem. Okay, so solving an eigenvalue problem may be more difficult than solving a minimization problem. So but if you have any kind of estimate on mu and L, then you which may be a cheap estimate, okay, which may be computed fast, then you get some idea of the convergence. Okay, now let us prove a result then, when we have both convexity and smoothness, lemma f. So f from Rd to R convex and L smooth, then for all x, y in Rd, we have 1 by 2 L Fy minus grad Fx is less than equal to Fy minus Fx minus grad Fx y minus x, and right, so and we have 1 by L grad Fx minus grad Fy minus grad Fx y minus x. Okay, so these are the intermediate results which we will find it useful at some point. So let us call this small a and this as small b. So to prove a, okay, so fix x comma y in Rd and start by using convexity and smoothness of f and then we will have Fx minus Fy. We can add and subtract Fz here. So this is Fx minus Fz plus Fz minus Fy. So this will be less than equal to grad fx x minus z plus grad fy y minus z minus y plus L by 2 z minus y squared. Okay, why is that? So fx minus xy, we added and subtracted that fz, and then we say that this is less than. I don't see where we used convexity here. I only see L, right? So that seems like we used smoothness. And smoothness smoothness for the second term I see, which is this. So fz minus fy is less than equal to this, right? But what happened to this guy, right? I mean, if I have used smoothness, then where is the L term here, right? L by 2 x minus z I was expecting here. Seems to be some. Let me check this to. Okay, it's just a simple convexity, right? Okay, that's right. So we are using the simple convexity, which was like fy greater than equal to fx plus grad fx y minus x, right? So the second one, the first one seems to be convexity, this one. So we will try to like figure out the first one now. The second one seems okay. Second one is the smoothness. Okay, so let us see the first one, and we have to change the inequality maybe. So we have used the smoothness, and yeah, so I will just steer a little bit what could be the correct way. So fz comes there. It seems like fx greater than equal to. Okay, so it seems like one second. No, the because in the inner product I see x, right? If in the inner product I see x, then it must be starting with z. Because remember, the grad is computed on the same variable as this term, right? So this will be x plus grad fx z minus x, right? So convexity is for all x and y, right? So I'm allowed to choose z here, x here, z here. But the only thing I have to make sure is these ordering are correct, right? So if I have fx, then it should be grad fx, and then z minus x, and so on. Okay, so this comes from the convexity of f. Okay, so this is convexity of f. First order characterization of convexity of f, okay, which means that any tangent drawn is a global lower bound of the function, right? So these are the things, that's why we did convexity and everything, right? Any fz value is greater than equal to the value taken on the plane, right? So now we have to figure this out. So fx minus fz, and this guy goes here, it's negative, so z minus x becomes x minus z. So it seems okay. Okay, so this implies fx minus fz is less than equal to negative of this, right? So let me do this one more step. But negative I can observe here or here, but it's better to observe here. So this implies fx minus fz is less than equal to grad fx x minus z. So all this is when using convexity of f. Okay, so this guy is convexity of f we have done just now. These are from convexity of f, and these guys are smoothness, L smoothness. Okay, so we have figured this out. Right, so so that makes sense. Okay, what we wrote is correct. Now, and what we are supposed to prove, we have to go there, right? And so this is the starting of the proof, and we are supposed to reach there. In fact, we have written is fx minus fy, right? So this is what we see here, right? Fx minus fy or fy minus fx, and yeah, since we started from there, let us like first kind of figure that out where we are going, right? So what we have is fy minus fx is must be greater than equal to 1 by 2l grad fy minus grad fx plus gradient fx y minus x. This is what we can, right? And if I apply by the negative, I'm just trying to relate to this, right? So we started with this. So if I apply the negative of that, so we had fy minus fx here, and this is same thing as saying fx minus fy is less than equal to 1 by 2l grad fy minus grad fx plus grad fx y minus x. Okay, I wrote this just to see where I'm going, right? Like I started with this, so perhaps I'm going to reduce to these two terms, right? So I had the first step where I have fx minus fy is less than equal to grad fx. I don't see any of the terms that I need, but we need to work a little bit, right? So far what we have is I have is grad fx y minus x, but what I have so far is grad fx x minus z, and I have grad fy z minus y. I have some term in L, but that's z minus y, but that okay, but that also doesn't correspond directly to here, right? Because the function is L smooth, so so the difference could be used maybe. Okay, so let us see the next step in the proof then. Yeah, it's a little bit here tricky because what it says now is like maximize. So to make this bound tight, okay, minimize the right hand side with respect to z. Okay, that's interesting. So we will minimize the right hand side with z. Okay, so minimize right hand side with z to make the bound tight, to get the tightest bound. So if we do that, then this is linear in z, right? So I mean it's a quadratic in z, right? So if it's quadratic in z, then just doing a gradient equating to 0 should be okay. Okay, because it's a quadratic in z, right? Why it's quadratic in z? Because you have the L term which is positive. So all the focus is here, right? This is your quadratic term, quadratic term will dominate. As a function, the quadratic term will dominate, and we have seen that in quadratic programming, what we are supposed to do is minimize x transpose px. That's our quadratic program, right? And we have seen, I mean, we can do it right now, right? So this is convex. Okay, let us define this to be fx. So fx is convex when what is the characterization on P? P is positive definite, right? P is positive definite. So as a function of z, you can see that the terms that you have, the first term is linear in z. Okay. So what quadratic program says is even more general, right? Not just the first term, you are allowed to have x transpose b plus c also. Okay. So this is the full quadratic thing. But if you do the second order check for convexity, second order check says that the Hessian must be positive definite. If the Hessian is positive definite, then the function is convex, right? So I take first derivative and then second derivative. I found out that the second derivative of this is P, matrix P. And if P is given to be positive definite, then the Hessian is positive definite because the Hessian is P, and this is necessarily convex. If it is convex, then gradient of this equating to 0 will give me necessarily the minima. Okay. So this is, if we are supposed to minimize this to get a tighter bound, we want to understand what type of function this is in terms of z. So if I take a derivative equate to 0, that is good enough, or something more need to be done, because if it is not convex, then it could be like this. So the derivative being 0 can happen at many places. So then I may not be able to say which is the best z, unless the points where the derivative is becoming flat is like finite, then I can check and so on. But this is quadratic in z. Why is that? Because this, if I expand, this is the whole thing is of the form this is of the form sum x transpose px plus x transpose b plus c. In form of z, it will be of the form z transpose some matrix times z plus z transpose b plus c. So I can do this quick thing for you. Okay. So what does this mean is, if I see that as, so inner product of grad fx with x minus z, that's just x minus z transpose grad fx, and then the second term is z minus y transpose grad fy, and then plus L by 2 of z minus y transpose z minus y. So if we rearrange this, so this is x transpose grad fx minus z transpose grad fx plus z transpose grad fy minus y transpose grad fy. L by 2, this is z transpose z minus L by 2 y transpose z minus L by 2 z transpose y plus L by 2 y transpose y. I'm just doing it to tell you that this is of this form only, okay? But I have to do it once at least. So let us pick the term that is of the form square, like where x and x are there, which is in this case is only one of the term is this guy, right? So this is of the form z transpose. I can put L by 2 identity. So this is my matrix P, z, and then I will collect all those of the form z transpose B. So all those of the form z transpose B are these guys, right? Z is here, Z is here, Z is here, and this is also Z transpose Y, or Y transpose Z is the same thing. Okay. So, this gives you the Z transpose B form. So, this is like Z transpose, and then you add all this grad fx plus grad fy plus L by 2 is L. So, L y. Okay. So, this is plus L y. This is my B, this is my P, this is my B, and then the remaining term is constant, right, independent of Z. So, in the constant term here is this guy, which is Y transpose grad Fi plus L by 2 Y transpose Y. So, this is our C. Which one here? So, inside its first one is minus, right, and second Y is Fy is plus, and the third and fourth again it's minus. So, this is a quadratic in this is a quadratic optimization problem, right. Now, we are supposed to minimize this, and minimizing a quadratic I mean whatever it be, right. I am just saying it is I am saying it's quadratic, but even if you do not know it's quadratic, if you have to minimize this, first step you will do is that you want to know whether it's convex or not. So, since it looks differentiable in Z, you will take double derivative because it's easier, and see whether the Hessian is positive definite. So, if I take a double derivative of this, right, if I take first derivative, constant goes away, and here only B remains, okay, and here Z L by 2 remains, Z L by 2 identity remains, and then if I take another derivative, then I will be left with only P, because this constant now goes away. So, hence the Hessian of this, let us say this is Fz, then the Hessian of Fz is just P, and P in our case is L by 2 identity, and indeed L is positive. So, this is positive definite, because identity matrix is positive definite, any positive multiple of identity matrix is positive definite. So, this implies Fz is convex. So, this implies that whatever all those points Z for which Fz is 0 are necessarily a minimizer. Okay. So, this is the reason why we will just take a derivative, equate it to 0, and we are for sure that after solving for that, the Z that we are getting is indeed the minimizer. Okay. So, let us try to now do that, right. So, take gradient of that and equate it to 0. So, from here you can see that, right. So, if I do the gradient equate to 0, then I let you decide that this will be the Z that you solve after simplification and all those will be this grad Fy minus grad Fx. Okay. So, if you solve for Z, then you are supposed to get this. Do you get that? This seems to be correct. Do you see that? So, if you take a gradient of this, so gradient of this is what, right? Gradient of this is L by 2 Z plus this guy, and solve for that, right. So, let us do that step, okay, the gradient step also, and then we equate it to 0, right. So, we are supposed to do this, right, grad Fx and equate to 0. So, if we do grad Fx, in this case let us say Fz, and equate it to 0. So, if we do grad Fz, then this is L by 2, let us say grad Fz is L by 2 Z, and the B only remains, right. So, Z, so only this remains, right. So, minus grad Fx plus grad Fy minus, oh okay, what was that, Ly, this was Ly, right, Z transpose Y, right, it was Ly. So, here we will have minus Ly, right, and we are supposed to equate it to 0, right, and solve for z, and that seems to be the case, right, unless I see a half extra which, oh, the half goes away, sorry, okay, because it's a quadratic, right, so there will be 2 coming and then this 2 will get cancelled, so there will be no half here, this is just Lz. We solve for that, right, so this is exactly what we have. If you solve for z, then we get this. So for this z, the RHS is tight, okay, the bound is tight. Okay, so let us put this z and make the bound tight. Okay, so substituting this in, let us say this is star, right, so substituting this in star, z in star, and after reorganizing, okay, I hope we will reorganize. So let us see fx minus fy, and I am going to suppose put this z there, right. So fx minus fy is less than equal to grad fx and x minus z. Yeah, I'm a little bit lazy to do all this. We have to put z there, right, which looks very big, right. So I'm thinking for a shortest possible, if it exists, right. If I do put z, what do I get? I don't see any cancellations also. Y minus 1 over L, okay, and then there is another z in the second term, and then also in the third term it matches after manipulation. You did that, right?
I assume the book did.
Yeah. Now if you did that, then it proves that all can do that, and hence I can just directly write. Okay, so it should be doable. This is all algebra, right? So it may take time, but these are not difficult things, right? So the only thing is, like, we are trying to save time. So what I can do is that I will write this first, and maybe we will try to see if it's evident. If not, then yeah, one has to put this and rearrange terms and see whether that works out or not. Okay, so this is x minus y 1 by L grad f y minus grad f x norm squared plus 1 by 2 L grad f y minus grad f x squared. So this is what we get after rearranging, because z is now substituted, so everything is seen in x and y, z is gone. But certainly some rearrangement has happened, and I am expecting that we should be able to do this. Okay, yeah, well, I see y there, and then L fy terms somehow get out of that, and actually the second and third term looks quite tractable because y gets cancelled in both of them. So this norm fy minus fx that you see in the second and third term might be easier, although it's not necessarily, I mean, there is still some work to be done. So should we do this, or should we try as an exercise then? Because if we do all possible algebra, then we won't be able to do too many things. I'm planning quite some things. Okay, so let us do that. Like, I'm not giving too many assignment anyway, right? So let us do this as an exercise. If you don't, then just write an email. Okay, it is okay to spend time in outside class. That's not waste, right? But class time is fixed. So you do this as an exercise. All of you will be able to do this, I'm pretty sure. I'm just saving time here. Okay, so this is your assignment. Okay, it's good to do some assignments, right? Okay, so then and this is equal to, and this is equal to, right. So this term is the same term. It's just that this is one of that. So this will be like minus half of that. Okay, so that's, I mean, these guys could have done even that step. I don't know why they left it, or is there something grad Fy minus grad Fx, grad Phi minus yeah. So then this step is just one reduction step. Okay, so they say that okay, this is like minus 1 by 2L. So this minus 1 by 2L Fy minus grad Fx. Maybe they wanted to show that this term somehow comes from the second and this term somehow comes from the third. And then, although this was an obvious step to just subtract these two terms. Anyway, so this is what we have, and this proves the A, I guess. Yeah, this is exactly what we were supposed to prove. We started with Fx minus Fy, and we said that Fx minus Fy is less than equal to, so I can just write this here as well, Fx minus Fy. So this is what we were supposed to prove, Fx minus Fy, this is less than equal to, yeah, we switched, right? So Fx minus Fy is less than equal to, because I will multiply by the negative, and then this grad Fx, since multiplying by negative, it will make x minus y, y minus x, and minus 1 over 2L, because I multiplied by minus. So this guy becomes 1 minus 1 over 2L Fy minus grad Fx whole square. Okay, that's verified. In case you are not sure, I mean, from my side it's verified. Okay, quality checked. Now you will do your own. Okay. This proves to, and to obtain 15, apply 14 twice by interchanging the roles of x and y. Okay, that's interesting. So to prove the B part, apply A part twice by interchanging the roles of x and y. This seems to be a good exercise. So to prove B, the hint is, so to prove B, apply A twice by interchanging the roles of x and y. Okay, this is also sounds like a good assignment to do, right? Because these things at the end of the day seems to be simple things, so you should be able to, there's no like deep concepts needed here. And interchanging the roles of x and y, and it says sum those at the end, in the end. Okay, and so it was actually very easy. So grad Fy, so if we apply that immediately, okay, since this is easy, I will take it. Okay, so Fy minus Fx minus grad Fx y minus x. So this was interchanging, I guess, x, and then another one was grad Fx minus grad Fy, Fx minus Fy minus grad Fy, x minus y. We applied A and B by interchanging x and y. Now we are supposed to sum, and if we sum, we get B. Okay, so you do a plus of this, and this implies B. That's exactly the proof we needed. Let us stop. Okay.